Welcome to our first learning video for OLI Mod 10. We're taking a look at quantifying variability relative to the mean. Remember to start that the mean is really only a good measure of center when we have a fairly symmetric bell-shaped distribution. The first few questions here you did along with OLI, but I do want to talk about number 3 for just a moment to make sure that we're all on the same page. I gave you 4 pieces of data here, 2, 3, 4, 7. The mean of that data set is 4. You're calculating each of the deviations from the mean. 2 is 2 units below that mean of 4, so its deviation is -2. I've got the rest of them filled in there. Then, if we're trying to get some idea of the average deviation from the mean, step 1 would be to add those values up, but when you do that, you get 0. And that will always have to be the case because that's the characteristic of the mean and that balancing point of distances, that the sum of all the distances below the mean, which gave us negative deviations, is always going to equal the sum of all the distances above the mean, which is our positive deviation. So that sum is always going to be 0. What are we going to do about it? Well, I think a natural inclination is, well, let's just take the absolute value. That will change all the negative values to positive. Absolute value is actually defined as distance, so a very natural thing to do here. So I've taken the absolute value of all those deviations, and now we can go ahead and find the mean, add them up, divide by 4. So we've calculated the ADM, the average deviation from the mean, 1.75 for this data set.
Except that's just not at all correct, is it? Because 2 plus 1 plus 0 plus 3 is in fact 6 and not 7. 6 divided by 4 is 1.5. So there you have the corrected values for this ADM for this data set. I'm going to send you back to the regular video now. So those incorrect calculations are going to come back in, but you knew better anyway. Sorry about that.
At this point, that means that we've got 3 different ways to measure variability from the mean. We started off taking a look at the range of all the data. That gave us the complete distance from beginning to end. We did maximum minus minimum to get the range. Then we took a look at the interquartile range, which gave us the distance just to get from the first quartile to the third. So we calculated that, Q3 minus Q1. And now, of course, we've taken a look at the average deviation from the mean, the ADM. Certainly the range and the interquartile range fall a little bit flat when we're thinking about the mean as a measure of center range because it's not taking into account any of the data besides the endpoints. And interquartile range is a great measure of variation when you're using the median as your measure of center. But for the mean, we're going to look in a different direction. The next one we're going to look at is hopefully some motivation as to why we don't just stick with this average deviation from the mean, the ADM. We usually use something a bit more complicated, the standard deviation. Why do we do that? Well, hopefully this exercise will help you understand. So we're going to use StatCrunch to calculate some things for each of these data sets. So let's go ahead over to the right hand side here. Let's open up our StatCrunch spreadsheet and I'm going to put each of these data sets into my spreadsheet. Remember that if we click up on the name of the column there, we can input our own name and then just put in each value of that data set. var2, let me call that one B, just like is on the paper, and then put in each of those data values. All right. The first thing we're asked to do is find the mean of each of that data set. Hopefully you remember how to do that in StatCrunch. Maybe pause the video here for a moment and just make sure you can do that on your own. Okay, here I go. I'm going to click on Stat, Summary Stats, Columns. I want both of my columns, and I'm just looking for the mean right now. So let's get those values. All right. The center of each of those data sets is exactly the same. They are both 2.5. So I'm going to note them over on my worksheet here. Let me get my pen for just a minute. There we go. All right. Notice that I'm using our notation. We're going to assume this is sample data for the moment. So our symbol is X bar, but we've also put a little subscript on to denote which of the data sets it is coming from. Okay, so each of these values is 2.5. Now, to get some sense of the variation of each of these sets, let's go ahead and make a dot plot. So again, maybe pause the video, make sure that you can make that dot plot. I'm going to do it here and then pull a photo on into my worksheet. Okay, so hopefully we all have the same dot plots over here, the dot plot for data set A and that of data set B. If you didn't remember, over in StatCrunch, it was your graph option and then choosing dot plot. And our question here is, do you think these two data sets have the same amount of variation? So we saw that they both have the same measure of center at 2.5 right here. And then as we take a look at that data spread around center, do you think they should have the same amount of variation, or should it be different? And I don't want you to think about which one would be larger and which one would be smaller, because that's maybe a little beyond. But for right now, do you think they should be the same, or do you think they should be different? Well, when I do this in class, most students say that they think the numeric value of variation for these two data sets should be different. But let's see what happens with the range and with the ADM. So range, we know, is maximum minus minimum. So for data set A, 4 minus 1 is 3. We've got a range of 3. And for data set B, 4.5 minus 0.5 is 4. So that is an indication that maybe the variation of these two data sets should be different. Let's go ahead and see what happens when we do the ADM. So I'd like everybody to pause the video for just a moment. We've already talked about the ADM, so find the ADM for each one of these data sets. Notice this distance to the mean here, distance, so there's our absolute value that helps us in the ADM. X is our symbol for just any old piece of data, so X will be 1 in this row, and then X will be 2 in this row, so on and so forth. And remember that our X bar value is 2.5 for each one of these data sets. Okay, complete your values and then come on back. All right, so hopefully we all came out with the same values here. The ADM for each of these data sets is exactly the same. We looked at the dot plots. I think most people would say they think the variation from the mean should be different for these two data sets. We saw in the range that we had a different value, but if we just stick with the range, that doesn't account for all the data sets in between. So we're looking for something a little more detailed that will take all of the data into account. But we see that the ADM came out exactly the same for these two data sets. So hopefully this at least gives you a little motivation for why we might calculate variability around the mean in a different way than using the ADM. So the thing that we're going to look at calculating now is called the standard deviation. I'm going to take a look at the formula here, although in practice we will use StatCrunch to calculate our standard deviations, but this formula really does go along with how it is calculated, so I do want to look at this formula. First off, we're going to be calculating the standard deviation of sample data. There actually is a slightly different formula if you're dealing with population data, but if you are, then you don't need the science of statistics, right? The science of statistics is using analysis of sample data to draw conclusions about your population. Okay, so the symbol for our standard deviation of sample data is S. And what we're going to do is we're going to find all of those deviations to the mean. Each piece of data X minus the mean X bar. But rather than doing the absolute value to take care of those negatives and positives like we did before, we're going to square them, and then at the end we'll have to square root everything to undo it. The reason we're doing this, it places a little heavier emphasis on data values that are far from the mean. And so in doing this, our data set B that has some data far away from the mean is going to come out with a slightly larger standard deviation than data set A. Just like we do for the ADM, after we find all these values, we add them up. This is a capital Greek letter sigma, and it tells us to add. Every time you see this symbol, it's telling you to do something. It's telling you to add together the values you have, or in other words, find a sum. All right, so it's just really mirroring what we did up here with absolute value, except now we're using the square. What do we do after we add them up? Well, we divide by the number that we have. Little n is our symbol for the size of a sample, the number of data pieces that we have collected in our sample. Now, we actually don't stop there though. If you stop there, it turns out that the standard deviation comes out all the time a little bit too small, and that makes it biased. If you're always wrong in the same way, then that is exactly our definition of bias. So to make this value a little bigger, to better represent the standard deviation of the population it came from, we make this denominator a little bit smaller. And instead of dividing by just n, we divide by n minus 1, okay? But again, the reason we do that, smaller denominator gives us a bigger overall fraction, and that is done to better estimate the standard deviation of the population that our sample came from. Okay, let's just take a quick look in StatCrunch and see how this is going to work. Stat, summary stats, columns. Just like we did for our measure of center earlier. I want to use both columns A and B, and I want the standard deviation. Compute, and there we have it. Our standard deviation, let me just add that in here. Standard deviation for data set A is 1.29. And our standard deviation for data set B is 1.63. Okay, next thing we're going to do is go back to our serial data and see what happens there.